Example 12. The sequence open bracket 3 over n plus 5 close bracket is decreasing because 3 over n plus 5 is greater than 3 over n plus 1 plus 5 equals 3 over n plus 6. And so a is greater than n, a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. Sidebar, the right side is smaller because it has a larger denominator. Example 13. Show that the sequence a sub n equals n over n squared plus 1 is decreasing. Solution 1. We must show that a sub n plus 1 is less than a sub n. That is n plus 1 over n plus 1 squared plus 1 is less than n over n squared plus 1. This inequality is equivalent to the one we got by cross multiplication. N plus 1 over n plus 1 squared plus 1 is less than n over n squared plus 1. Suppose which is interchangeable with open n plus 1 close open n squared plus 1 close is less than n open bracket open n plus 1 close squared plus 1 close bracket. Next line, n cubed plus n squared plus n plus 1 is less than n cubed plus 2n squared plus 2n, and 1 is less than n squared plus n. That's the next line. Since n is less than, since n is greater than or equal to 1, we know that the inequality n squared plus n greater than 1 is true. Therefore, a sub n plus 1 is less than a sub n, and open bracket a sub n close bracket is decreasing. Solution 2. Consider the function f of x equals x over x squared plus 1. F prime of x equals x squared plus 1 minus 2x squared over open x squared plus 1 close squared equals 1 minus x squared over open x squared plus 1 close squared is less than 0 whenever x squared is greater than 1. Thus f is decreasing on the interval 1 to infinity, and so f of n is greater than f of n plus 1. Therefore, open bracket a sub n close bracket is decreasing. 11. Definition. A sequence open bracket a sub n close bracket is bounded above if there is a number m such that a sub n is less than or equal to big M for all n greater than or equal to 1. It is bounded below if there is a number m such that m is less than or equal to a sub n for all n greater than or equal to 1. If it is bounded above and bounded below, then open bracket a sub n close bracket is a bounded sequence. For instance, the sequence a sub n equals n is bounded below. Open a sub n is greater than 0, close but not above. The sequence a sub n equals n over open n plus 1 close is bounded because a sub n is greater than 0, that's less than 1 for all n. we know that not every bounded sequence is convergent. For instance, the sequence a sub n equals open -1 closed to the power n satisfies a sub n is greater than or equal to -1, but less than or equal to 1, but is divergent from example 7. And not every monotonic sequence is convergent. Open a sub n equals n as a sub n equals n approaches infinity. But if a sequence is both bounded and monotonic, then it must be convergent. This fact is proved by theorem 12, but intuitively you cannot understand why it is true by looking at figure 12. If open bracket a sub n close bracket is increasing and a sub n is less than or equal to big M for all n, then the terms are forced to crowd together and approach some number big L. Figure 12. The proof of theorem 12 is based on the completeness axiom for the set of all real numbers, which says that if big S is a non-empty set of real numbers that has an upper bound M open, that is big M open x less than or equal to big M for all x in big S close, then big S has a least upper bound B. This means that B is an upper bound for big S, but if big M is any other upper bound, then B is less than or equal to big M. The completeness axiom is an expression of the fact that there is no gap or hole in the real number line. 12. Monotonic sequence theorem. Every bounded monotonic sequence is convergent. Proof. Suppose open bracket a sub n close bracket is an increasing sequence. Since open bracket a sub n close bracket is bounded, the set big S equals open bracket a sub n given n is greater than or equal to 1, close bracket, has an upper bound. By the completeness axiom, it has at least upper bound big L given epsilon greater than 0. Big L minus epsilon is not an upper bound for big S, since big L is the least upper bound. Therefore, a sub big N is greater than big L minus epsilon for some integer big N. But the sequence is increasing, so a sub n is greater than or equal to a sub big N for every n greater than big N. Thus, if n is greater than big N, we have a sub n is greater than big L minus epsilon. So 0 is less than or equal to big L minus a sub n, which is less than epsilon. Since a sub n is less than or equal to big L, thus the absolute value of big L minus a sub n is less than epsilon whenever n is greater than big N. The limit as n approaches infinity of a sub n equals big L. A similar proof using the greatest lower bound works if open bracket a sub n close bracket is decreasing. The proof of theorem 12 shows that a sequence that is increasing and bounded above is convergent. Likewise, a decreasing sequence that is bounded below is convergent. This fact is used many times in dealing with infinite series.